In the previous section, we used FPGA clocks to determine the execution time of the individual VIs and functions on the FPGA VI block diagram. By the end of this module, you will be able to troubleshoot single-cycle time loop errors. Okay, so in this section, we're going to talk about how to troubleshoot single-cycle time loop errors. So the single-cycle time loop, the contents that are inside it, need to execute within a single clock period for it to work. So some things to keep in mind in light of this. So some VIs and functions can't be used in that loop at all, right? Because some VIs and functions are not going to be able to execute within a single clock period. For example, if you take a look at analog input and analog output, so most analog input and output hardware is going to take multiple clock ticks to be able to either read that analog input or output something to an analog output. So we saw earlier the 9211, it takes 70 milliseconds for the conversion rate. So because it takes that long and it won't be able to happen within a single clock period, those types of functions can't be inside the loop. Now, digital inputs and outputs, on the other hand, can usually execute within a single clock tick. So those you can put inside single cycle time loops. Also, you can't put nested loops in there. So you can't put a while loop in there or for loop or time loop because those are going to take multiple clock ticks. Also, a loop timer and wait express VIs, those are going to take longer than a single clock tick, right? So those won't work inside a single cycle time loop. Also, you have to think about other objects or functions that require more than one clock cycle to execute. For example, the divide function is a pretty heavy-duty function, and it's going to take more than one clock cycle to execute, so you won't be able to use that function or the quotient and remainder function.
So you can put a for loop in a single cycle time loop if the for loop contains numeric, Boolean, or comparison operations and uses only auto-indexed tunnels. However, objects that generate or contain state, such as shift registers, feedback nodes, or VI calls are not allowed in for loops within a single cycle time loop.
So if you want a more detailed list of unsupported objects, you can go to the LabVIEW FPGA help and find a list of those there. So what we see on this slide is a code generation error window. This window is going to show you unsupported objects, and this will pop up when you first compile an FPGA VI. So when you first compile the FPGA VI, before it even gets to the compilation stage, it starts generating intermediate files. So while it's generating these intermediate files, it'll know right away if you put an unsupported object in there. Okay, so you'll be able to catch some of these mistakes very early on. So in this case, we tried to compile a VI, but while it was generating those intermediate files, it noticed that, oh, we've got some objects in the single cycle time loop that aren't supported. For example, you see the divide and also the FPGA IO node for an analog input. So if you were to double click one of those, it would bring you to the spot on your block diagram where you use that inside a single cycle time loop, and you can go ahead and correct it by removing it or replacing it with some other logic. So the single cycle time loop is limited by logic and routing delays in the FPGA circuitry. So for example, the code that you put inside your single cycle time loop, if the way that it's implemented on your FPGA, based on the logic and all the routing delays to connect that logic together, if all those functions are not going to be able to execute and all those delays are not going to be able to execute within a single clock tick, then that single cycle time loop is going to cause your compilation to fail. So if the total path propagation takes longer than one clock cycle, compilation fails. There's no way to predetermine the path length. So what you want to do is you just want to use best practices and try to reduce that path length before using your single cycle time loop. So you want to make sure your code inside a single cycle time loop is optimized and you're using best practices. So on the right hand side, you see a compilation status window that has failed. So if you take a look at that, notice that in the description there, the status says timing error, and also it says that the compilation failed due to timing violations. This is most likely because you have a single cycle time looped in there, and then you're telling it to execute at a speed, and all the code inside that single cycle time loop could not execute within a single clock tick. So in this slide, we see that same window that we saw in the last slide. Notice that if you have a timing violation, you can actually click this button called Investigate Timing Violation. If you select that button, it'll open up a dialog, and it'll show you what the exact timing violation was. So you can see the logic, routing, and total delay of each item. And one thing I want to show you real quick is if you look at that very top line, it's a little bit small, but you'll see that the requirement here is you needed that single cycle time loop, all the code in there, to execute within 12.49 nanoseconds. So we see that requirement on the first line. But if we look at the total delay of all the code inside there, we see that it's 27.47. Okay, so when we implemented our code on the FPGA, it took 27.47 nanoseconds, which is higher than the requirement of 12.49 nanoseconds that we set our single cycle time loop to. So because that delay was longer than the requirement, it's going to cause our compilation to fail. So this is a very useful window. You can look through those different elements inside that time loop, and you can see how long each delay took. And based on that, you can try to fix your single cycle time loop and just figure out how to optimize that code to actually make it fit inside your requirement. Or you can try to change your requirement to be something longer that would accommodate the amount of time it takes for your code to execute. So there's multiple ways of going about and fixing these timing errors. So based on that timing violation analysis window and the information you got from it, there's a couple things you can do to fix the timing violations. So one thing you can do is you can try to speed up the path by optimizing the code inside the single cycle time loop. So by optimizing the code in there, the code is going to take less time to execute, so maybe you can still fit it inside that single cycle time loop. Another thing you can do is you could select the slower clock for the single cycle time loop timing source. So if you select the slower clock for the single cycle time loop, then each clock tick is going to be a little bit longer. That way you can maybe accommodate some more time for your code to execute. Another way you can do this is you can speed up your path by moving some code out of the single cycle time loop. So maybe some of the slower code, you can remove it from your single cycle time loop and put it outside of it. And that way you're still able to optimize some of the code that you have in there to execute within a single clock tick. The other thing you can do is you can speed up your path by reducing its length even further by using a technique called pipelining, which we'll talk about later in this lesson. So on this slide, we see how we can also use the single cycle time loop to optimize sections of code. So for example, let's take a look at this while loop here. So on the while loop on the top, we see that we have an analog input node, and then we have some functions in there. So we have a multiplication, we have subtraction, and then after we've done some processing on it, we then send it out to an analog output node. So based on what we talked about before, we know that the analog I/O nodes can't not go inside a single cycle time loop because they take more than one clock tick. So what we can do instead is maybe we can try to optimize sections of code. So if we look at the bottom, we still have the FPGA I/O nodes for analog input and output, but we've made sure that those are not inside a single cycle time loop. And what we've done is we've taken this algorithm and we put the algorithm inside a single cycle time loop. So that algorithm, that section can all execute within a single clock cycle. So notice that the loop condition terminal inside the time loop, it has a true constant connected to it. So what that means is when we get to this single cycle time loop, it's going to execute the code in there once, and then it's going to exit, and then it's going to go on to the rest of your code. So this is a handy way of optimizing sections of code and making them execute within one clock cycle. Okay, so at this time, if you're able to, it's a great time to be able to do exercise 6.2, and in this exercise, we'll walk through fixing a couple of these single cycle time loop errors that we've just talked about. For now, I'm going to do a walkthrough of this exercise for you to follow along with. Okay, so let's step through this exercise, and we will take a look at some single cycle time loop errors and troubleshoot them. Okay, so here we've got our FPGA target. I'm going to go ahead and open up Investigate SCTL Errors. And let's look at the block diagram. Okay. So looking at the block diagram, do we see any problems right now with this single cycle time loop? Well, I see two of them right away. So one of them is this analog input I/O node. So remember, analog input I/O nodes will take much longer than one clock tick. So because it takes longer than one clock tick, it's not going to work inside a single cycle time loop. Also, we see a divide function. So remember, divide is a very large function, and it actually takes more than one clock cycle to execute. So this also will not be supported inside a single cycle time loop. So just to see what would happen, let's go ahead and try to compile it anyways. So I'm going to hit run, and I'm going to try to compile it. So now it's generating intermediate files. And during that process, so before it even tries to compile it, when it tries to generate these intermediate files, it'll find out whether there are any unsupported objects inside your single cycle time loop. So notice that one, we've got divide. So if I double click this, it'll bring me to the divide. So it's showing me that this is unsupported. And then also, if I click on FPGA I/O node, it'll also tell me the details that this object takes more than one clock cycle to execute. I can also click on Show Error. and it will show me where it is. Okay, so the way that I would fix this is I would move this outside of the single cycle time loop, and I would replace this divide function with something that's that does the same thing but is not as large. So I would replace that with a scale by power of 2, because I've got a division by 4. That's the same thing as scaling it to a power of 2 of negative 2. So I'm going to close this VI. I'm going to close this box and close this, and I'm going to go to a version of this where I fixed that error. So I'm going to open this up. Let's go to the block diagram. And now notice that here I have moved this outside of the single cycle time loop, and I've also replaced the divide with a negative 2 here. And I'm optimizing this part of the code by doing a true to the loop condition. Okay. So next thing I'm going to do is let me double click this time loop and set the clock rate that I wanted to execute at. So in this particular project, we've got our default 40 megahertz, but I've also created a 80 megahertz derived clock and also a 200 megahertz derived clock. Okay. So right now I'm going to go ahead and select this 200 megahertz derived clock and try to compile this single cycle time loop at a 200 megahertz clock, which is very, very fast. So I'm going to click OK. And then I'm going to hit run and try to compile this. Okay. So most likely, I'm just going to tell you now that this is going to fail because 200 megahertz is very quickly is a very fast clock, and most likely this functionality will not be able to fit inside there. So let's see what happens when we try to compile this. So let me go ahead and save some changes, compile it, and now let's see what happens. Okay, so we've done this compilation, and now we see that the compilation has failed, and we notice that the status here is a timing error. So if there's a timing error, we're going to get this button that will appear, and it'll be investigate timing violation. So let's go ahead and click on it and see what information we can get. Okay, so notice we've got this path requirement, and because we've specified a clock of 200 megahertz, we only have 5 nanoseconds for all that code to finish. Okay, so if we take a look at this, the total delay we have for our code is 9.11. Okay, so it looks like it takes almost twice as long for our code to execute than is required. Okay, so at this particular speed, well, there are several ways to fix the timing error, and the way that we can try fixing it in this particular exercise is we can increase the clock, or we can make the clock run at a slower speed. Okay, so let's go ahead and do a close, and I'm going to close this compilation window as well, and let's go to our block diagram. So in this case, maybe we don't necessarily need this code to execute at a clock rate of 200 megahertz. So we can double click this, and in this exercise we're just going to choose a slower clock of 80 megahertz. And based on what we saw in that previous timing violations window, we can do some calculations, and we can see that our code will definitely fit inside 80 megahertz clock. Okay, so we can take 80 megahertz, click OK, and if I were to run this, I'll just let you know right now that at 80 megahertz, that code will be able to compile. We saw that there was a total delay, I think, of about 9 nanoseconds. So if you do 1 divided by 9 nanoseconds to figure out what your maximum frequency that will compile at, 80 megahertz is well below that. So this should compile. So I'm not going to take the time to compile it here, and you can just take my word for it, or you can do the exercise. Okay, so let's go through these discussion questions real quick. So why is the 9234 analog input FPGA I/O node not supported in a single cycle time loop? So remember, the analog input FPGA I/O node is going to take more than 1 clock tick to execute. Therefore, it cannot work inside a single cycle time loop. How can you estimate the fastest derived clock rate with the single cycle time loop will successfully compile? So if you remember what we just did in that exercise, we were able to try to compile it at 200 megahertz, right? And it failed. And we went to the timing violation window, and we saw how much it failed by. And we saw that the total delay of our code inside there was about 9 nanoseconds. So to find the fastest possible clock rate that our current code could go at, we would take that 9 nanoseconds and we would do 1 divided by 9 nanoseconds to get the frequency, right? So if you did 1 divided by 9 nanoseconds, that would get you something about 111 megahertz. So if you wanted to pick a clock rate that it'll compile at, you can try to do something that's 111 megahertz or slower.